So welcome everyone to the Tartan Planning Series. Today we're excited to hear from Professor Geoff Hollinger. Geoff Hollinger is an associate professor in the Collaborative Robotics and Intelligence Systems Institute and the School of Mechanical, Industrial, and Manufacturing Engineering at Oregon State University. He has previously held research positions at the University of Southern California, Intel Research, University of Pennsylvania's GRASP Laboratory, and NASA's Marshall Space Flight Center. He received his PhD and master's degree in robotics from Carnegie Mellon University and his bachelor's degree in general engineering along with philosophy from Swarthmore College. He is the recipient of the ONR YIP Award and the NSF Career Award, and he has served as associate editor for the Autonomous Robots and IEEE Robotics and Automation Letters journals. Thank you, Professor Hollinger, for taking the time to speak with us, and the time is now yours.
Great. Thank you so much, Brady, for the introduction and for inviting me today. I'm happy to talk to you guys for about 40 minutes, and then we'll have plenty of time for discussion. So today I wanted to talk about decision-making for marine robotics and planning, decision-making, a little bit of learning as well. We won't be talking about building the vehicles because that's not really what I do, and it's not really what you guys do as well. But we're going to talk about giving the vehicles intelligence and autonomy capabilities through better planning, learning, and decision-making algorithms. So first, we'll talk a little bit about the kinds of marine vehicles that are in place and out in the ocean, out in lakes and rivers and things like that today. Up in the top left is a Slocum glider. This is one of the sort of most prevalent, commonly used underwater vehicles right now. The Navy has, I've heard, probably hundreds of them out, though of course we don't know the exact numbers for sure. And so these vehicles, they're buoyancy controlled. And so they're able to change their buoyancy and move up and down in the water column. And they have wings that allow them to create a control surface to move around through this buoyancy control. And the thing that's really great about that is it makes them very low powered so they can have very high endurance and stay out for long periods of time. And these kinds of vehicles can do things like monitor harmful algae blooms, which you see some growth down there in the bottom left, or also look at physical oceanographic features that are of interest to scientists like coastal upwelling fronts and things like that. And we're going to talk a lot more about that in the presentation today. Now, on the other end of things, you can also think about infrastructure maintenance and inspection. In the bottom middle there, some of you may know Michael Kess over at CMU or have worked with him. This is a hovering autonomous underwater vehicle that can do things like ship hull inspection and infrastructure inspection. And so this is another marine robotics problem that requires planning and decision-making because the vehicle needs to know where to go in order to inspect a surface or to generate a 3D reconstruction of the surface or to monitor the environment. Additional applications of this in the top right, there was a large fish kill. This is a picture of it in Redondo Beach Harbor in LA. And what we did was we actually brought underwater vehicles into the harbor and measured the oxygen levels in the water. And we found that the way that the harbor was built created some sort of physical phenomenon that led to hypooxygenation, so depletion of oxygen in the environment. And basically, we recommended that they rebuild the harbor, or add an additional outlet to the harbor in order to try to avoid these kinds of things. And lastly, in terms of surveillance, security, there's an example of a police officer that's using a propeller-driven AUV to try to do things like look for drug smuggling or look for unexploded ordnance that may be on the bottom of the ocean, or look for illicit objects or even potentially bodies underwater. So there are a number of applications for these kinds of vehicles, and in all of these different applications, the robot is gathering information about the ocean environment. And sometimes that information might also be augmented by satellite data. And so there's additional data that can be brought into play and used for this. Now, the issue that I'm going to talk about today and some of the solutions that we've developed are trying to improve the efficiency and the cost effectiveness of some of these underwater monitoring type of practices. So right now, the current state of practice, the way that most people do it is to have an operator pre-specify waypoints for the vehicle. So for instance, the Slocum glider here may be monitoring the ocean. A bunch of scientists will say, here are the waypoints that the vehicle should go to. And then a team of experts looks at the data. The vehicle really can only transmit data back when it's on the surface, with the exception being a sort of very low bandwidth, high latency acoustic communication that you can do underwater. With vehicle surfaces, it uses satellite phone or radio to sort of beam back that information. The experts look at it and they give the vehicle more waypoints. This is often done in a very ad hoc manner. It really requires a lot of expertise and a lot of experience from the humans and from the experts in order to get the vehicle to perform, worthwhile trajectories. And the goal for us that we want to move towards is marine autonomy. And what marine autonomy entails is in situ decision making. We want the vehicle to be able to sense the environment and make intelligent decisions based on that sensing information that it gathers. We want to be able to have robustness to errors where something can go wrong. Obviously, if it's a catastrophic error that requires, the vehicle sinks or something, they wouldn't be able to recover from that. But something like part of the wing being broken off or the propeller jamming, we may be able to recover from these kinds of errors. So we want to be able to do that as well. And ultimately, what we want this to lead toward is the idea of shared autonomy with the technicians, where we have an AI system that's helping to make decisions using the advantages of computation and of robotics. And that's complemented by the expertise from the oceanographers. They have years of experience and they understand the science. And so what we want to be able to do is sort of meld these. And the big advantage of this is that now we can scale up. The current state of practice is you need one or more, usually lots of operators for one or a couple of these assets. We want to be able to have one operator and 100 assets or 1,000 assets. And to be able to do that, we need much higher levels of autonomy than what we see in the state of practice today. So I'm going to talk about two sort of research thrusts that get towards this idea of marine robotic autonomy. I'm going to talk about an example in multi-robot information gathering with heterogeneous assets. So we're going to talk about how do you coordinate surface vehicles with underwater vehicles. I'm actually going to use the Slocum glider here that I've been alluding to already. And then in the second part, we're going to talk about semantic navigation. And the idea behind semantic navigation is that we can take words, instructions in natural language, and translate them into executable plans by the robot. So this is how we're going through these two threads. We're going to try to make robotics more autonomous and also more user-friendly, and also allow for the capability of having a less trained operator or fewer operators controlling more robots in a larger system. So let's see how we're able to do that. All right, so let's talk a little bit more about the domain of interest. And this is going to be the domain of interest throughout the talk, but you can think about other applications as well. You can also think about aerial vehicles and ground vehicles and other modalities as well. But let's talk about this particular underwater application. So ocean monitoring generally can provide insight into a number of ocean features that are of scientific interest, and also of anything that is interesting to scientists is also most likely interesting to the Navy, because they want to make sure that they can secure the battle space and have access to the ocean. So they need to understand the conditions as well. So both in terms of military and scientific applications, we're interested in things like coastal upwelling fronts. So upwelling is when nutrient-rich water comes to the upwells to the top of the ocean, and that leads to a temperature inversion where you have colder water at the surface and warmer water below. And this leads to some very interesting biological events as well that marine biologists are interested in. I mentioned hypoxia, so that's situations where there's oxygen depletion in the water. That can be an environmental disaster if that happens in a particularly bad location. And then also things like chemical spills and oil spills, where we have situations where we may also have significant environmental impact. So these are the kinds of things that we want to be able to monitor. And traditional methods for long-term ocean monitoring are very expensive and really quite inefficient. And so if you want to rent out a research vessel, I think this number keeps going up. I had an oceanographer say $50,000 the other day. I was saying 30,000. I guess I'm a little bit out of date. But renting out a deep ocean research vessel to try to gather information and get sensor data is very expensive. It can be up to $30,000 a day. And the Slocum glider costs about $100,000. So 4 days of operation of a ship, you're basically, you've paid for the glider. If the glider could go out and gather that data autonomously on its own without ship support. So autonomous underwater and surface vehicles, this is an example of the surface vehicle, a sort of autonomous kayak that was developed by one of my collaborators in oceanography here at OSU, can help reduce this cost, because then you just have to buy the vehicle and it can stay out potentially for very long durations. But the limiting factor is that, as I mentioned before, current levels of autonomy are insufficient for larger numbers of these vehicles unless you have a large number of highly trained operators. And there are only so many of those, and they're very busy and very expensive. So we'd like to be able to do this with less training and with more autonomy. So talking a little bit more about the vehicles, this is the Robotic Ocean Surface Sampler, which is called ROS, which is a little confusing to roboticists, named by an oceanographer. So ROSS as opposed to ROS. This was developed by my collaborator in oceanography, Dr. Jonathan Nash. Nice thing about these vehicles is you can get continuous satellite and radio communications because they're on the surface. You can get up to about 1 meter per second velocity, depending on how much seaweed is messing you up in terms of the propellers. And so in the experiments that I'm going to talk about, we're going to have 2 of these surface vehicles. And then the other asset that we're going to talk about is the Slocum glider, which I've already talked about fairly extensively. These are built and sold by a company, Teledyne Industries. There are hundreds of them out there. The pretty common asset, particularly in the Navy and scientists. They are able to get satellite data connection when they're on the surface. And usually that only happens about every 2 hours. You can have them surface as much as you want, but when they surface, they kind of have to stop collecting data and they have to go to the surface and go down to the surface. So you're interrupting your data collection in order to do that. And these are slower. They're about 0.4 meters per second in terms of velocity. And they get that velocity by controlling their buoyancy and sort of flying through the ocean. And in the experiments I'm going to talk about, we have 4 of these assets. So think about this team. 5 to 10 assets, surface vehicles, underwater vehicles. We want to collect ocean data, and we want to collect ocean data in the right place that is of the most value to the oceanographers and the scientists. How do we go about doing that? Well, from robotics, we can use automation to reduce the operator load during sampling tasks. And the way we can do that is we can provide visualizations of the data in real time. And we also can provide suggested trajectories of where the vehicles should go in order to gather more information. I'm going to talk about how we can do that. And by doing that intelligently, we can improve the quality of ocean science data through this adaptive autonomous sampling, this autonomously adaptive autonomous sampling. And then from oceanography, we get the experience in manual sampling ocean features. Some of these operators have been doing this for decades, and the deep scientific understanding of the dynamic physical ocean processes. And from that, we can hope to improve the autonomy using the knowledge of the ocean processes in the decision-making. So as we're designing these algorithms, we want to use the expertise from the oceanographers to make the algorithms better as well. And I'm going to talk about how we can do that by tailoring the objective function to the science goals of what the scientists want. All right, so first, let's talk about the planning and the decision-making. The key challenge here is we want to be able to do adaptive control of, I'm going to say 5 to 10, this is 4 to 6, but in terms of the assets we have available, we want to be able to do adaptive control of heterogeneous assets. We want this to be scalable. We want to be able to handle this relatively large planning space. So those of you who work in multi-robot coordination, you know that if you have 1 robot, there's n dimensions. For 2 robots, it's n squared dimensions, the joint planning space for the entire team. And as you scale up, you get n squared, n cubed, n to the 4th. There's this exponential increase in the size of the planning space as the number of assets increases. So we want to be able to have scalability to handle this larger planning space. We want to have adaptability that enables the robots to adapt their behavior to new information as it becomes available. That's that idea of in situ decision-making and also robustness to errors. And also flexibility to be able to account for the realities of physical robot operation. And so if robots go down, if they break, if they move more slowly than expected because of seaweed biofouling, we want to be able to take those kinds of things into account. This is not a perfect environment by any means. And so the method that we decided to employ here and to develop for this kind of task is a variation of Monte Carlo tree search. So many of you have probably seen Monte Carlo tree search before, but the basic idea is that you build up a tree of possible partial solutions. And ultimately you expand the tree. In this case, the tree is expanded by adding waypoints to the trajectory. And then you simulate the policy. You need some objective function, which I'm going to talk about later. But you simulate the policy through that expansion, and you try to say, how good is this trajectory relative to the optimal trajectory or the objective function that I'm trying to optimize. And then you back propagate, which sort of tells you the value of all of these different partial trajectories. So some number of waypoints. So for instance, if I'm trying to plan a day ahead of time, each of those waypoints might account for about an hour of the mission. And I would build, or it could be a half hour, depending on what kind of granularity you're using. And so you build this tree up incrementally. And then you look at, all right, how good are these partial trajectories? And then you would probably try to focus on the most promising trajectories and build out those areas of the tree that seem to have good science quality, high quality data. So what MCTS allows us to do is leverage focused random sampling, where we're focusing on the most promising trajectories, and also exploits the smoothness of the search space. So we're sort of moving where there's a underlying gradient, essentially, that we're following to try to get to these better trajectories. It also leads to an anytime algorithm. So at some point, we'll have built the tree out enough that we have a full solution to whatever time horizon we're thinking about. And that gives us something that we could run on the vehicles. But then we can continue building out the tree to look for better solutions depending on the computational resources. And if you're doing this on a ground station, you probably have a desktop computer, something like that on the ship, or a shore station. You may have a server. If you're doing it embedded on the vehicle, you may only have something like a Raspberry Pi. So depending on the amount of computation you have, you're able to do more or less of this tree expansion. And so this allows us to do that. We can also incorporate sort of problem-specific heuristics in terms of how you grow the tree out and those kinds of things. So it's a very flexible, very nice framework. The other aspect of it is that it allows us to handle the planning space. And the way that we do that is by running an MCTS search. Those of you who are familiar with my work, you probably guessed how we do this. So you run an MCTS search on each of the assets, or for each of the assets, either on board or using the offboard computation. And then you leave that as fixed, and then you run the other asset basically in a sequential manner. So the first one plans, shares that information with the rest of the group. Second one plans, shares that information with the rest of the group, so forth and so on. So this iterative optimization sidesteps planning in the joint space. So now we just have linear computation in the number of vehicles. And so this will allow us to scale up to 10, maybe even 100 vehicles. Largest we've done is about 10 or 20. We also have adaptability because MCTS has been used in informative path planning tasks where things change in the environment. And also flexibility because it's simple to add or remove robots from the planning step, because if they're done, if they're out, you just simply don't plan for them, and everything else remains the same in the iterative optimization. So this is the technique that we're going to do. So we have a team of robots, 2 surface vehicles, and 4 gliders. We have a current belief of the environment, which we generate using a Gaussian process. So from the data that we have, and we can also incorporate satellite data into this as well, we get a representation of what the ocean environment looks like. And from the Gaussian process, we also get a representation of the uncertainty in that estimate. And so we'll see in a couple slides down how we take that and turn that into an objective function. So assuming that we have an objective function, think exploration, exploitation, hint, hint, think we have an objective function based on the Gaussian process. We have a single robot MCTS planner for each of these vehicles. And then we repeat that iteratively for each robot in the planning set. And then we can continue repeating that sort of round robin for a fixed number of iterations. And what comes out is a plan for all of these heterogeneous assets. The other thing that's nice about that is that the only planner that needs to know the constraints for each robot, so for instance, the constraints for the sloping gliders is different from the surface vehicles, is whatever planner is planning for that robot. So we don't need to have full team knowledge in order to do this, this plan. And so here's an example of the autonomy output. And this is, I'm also going to finally talk about this objective function that I've continued to hint at throughout the talk. So this is an estimate of what the environment looks like. So this is salinity. You're also seeing ocean currents from the vectors. So the salinity in the environment is a representation of the coastal upwelling front. So in the areas where of interest, there are going to be significant salinity gradients. So salinity is going to change a lot in these areas where there's an upwelling. And so what you want to do is you want to sense in places where there's high salinity gradient. That's your exploitation term. And you also want to sense in places where there's high novelty. So from the Gaussian process, we also have an estimate of sort of the uncertainty or the variance, the estimated variance in that estimate. So we also want to sense in places where there's high novelty. We use a cross product term to try to smooth that out and get places where both are useful. And this was sort of initially, actually, alpha 1 and alpha 2, those are scaling constants in terms of how much you care about exploration and exploitation. And of course, I have no great way of setting those. You have to do an empirical valuation or set those by hand. And this was initially our cost function, just alpha 1 and alpha 2. Then we added these other terms. So the cross product term just sort of makes it nicer, a little bit smoother in terms of balancing off the novelty and the salinity gradient. But then these other terms came out through discussions with the oceanographers. So one thing that the oceanographers wanted is they wanted the more recent data, the data that's coming sooner, to be valued more highly. So we added a temporal discount. That's sort of like a discount factor in an MDP. That was something that they wanted. They wanted to prioritize new information because the environment is changing. And so the near-term future is sort of more, has higher priority than the further off-term future. And then there's also this continuity measure, which is basically saying that when the vehicle turns, that actually degrades the quality of the information. And so we added this continuity term in there to try to prioritize straight paths. And these are the kinds of trajectories that you end up with. So here we have 4 vehicles. They're sort of spread out throughout the environment. They're able to cover the environment well. And they're also able to sort of focus on these areas where there are higher salinity gradients over in the right hand of the part of the map. And so the idea is that we're able to kind of balance exploration and exploitation by using this multifaceted objective function. We also developed a decision support tool for visualizing the ocean. This was done in collaboration with Julie A. Adams here at Oregon State, who works on human-robot interaction. And so basically, this is an example of the kind of imagery you would get. So this is temperature. You also can show salinity. And then the trajectories are also shown in this decision support software. And that allows for the operator to visualize what's going on. And so what the MCTS outputs is it outputs a trajectory for each of these vehicles. So for instance, here's one kayak that's out in the ocean. So it outputs a trajectory, and then the operator can say, yes, I want that trajectory, or the operator can say, no, I don't want that trajectory. For instance, it may run too close to a shipping lane or too close to land, or there may be some reason to reject it. And then the MCTS planner can replan at that point. So this kind of gives you a full user interface and decision support system for operating these kinds of things. So the really exciting thing about this is, just before the pandemic, we were able to get this in before 2020, thankfully. We were able to do a 10-day deployment in the Gulf of Mexico, and just now, things are starting to get back up where you can do these kinds of experiments again. But what we did was we were out in the Gulf of Mexico for 10 days in this particular deployment zone, and we were looking for upwelling fronts. And so we had a few different, basically sub-experiments that we did. One was to look at doing the robots under manual control. And that's the way that the oceanographers typically do things. So they typically are going to set waypoints. They're going to send the vehicles out to sort of look for these fronts. That's going to be our baseline. And what we had was 4 autonomy experiments. The 14-hour one was sort of a pilot shakeout study. And then 3 longer autonomy experiments where we changed the parameters around a bit in the objective function. And so what we're looking for here is we're looking for competitiveness with the manual control. We're really not trying to beat the manual control. We understand that the operators and oceanographers that we have are the experts. So what we want to be able to do is have the autonomy system be as good, hopefully, as the manual control case. And so this was the experiment that we did. These are the assets that we had. So we had a ship. So we used the data from the ship. The ship's also able to collect salinity data. We have 2 of these surface vehicles. Notice that the uptime is not perfect. Sometimes things go down, need to clean the engine, unbiofoul the seaweed, whatever. So all assets are not running at all times, but that's okay. Our algorithm is flexible enough to handle that. We have 4 glider assets, with some uptime each, and then also a drifter in the water that is uncontrolled that's getting us a little bit of additional information as well. And so here's an example of some front crossing, and here's what front crossings, and here's what they look like. So if you're a physical oceanographer, you would really, these 2D swaths are something that you look at very often, but those of us in robotics may not have seen them before. So this is what sort of the 2D representation of the environment is. PSU is salinity. And so what you see is there's sort of a high salinity region here and lower salinity regions around it. And so what this swath here shows is it shows an upwelling front. So here's an example where there's sort of a higher salinity region, and it's surrounded by lower salinity regions. And so we've sort of found the ocean feature, the scientific feature that we wanted to find. And this is on the 29th of May, 4th of June. We have another front crossing here as an example. 5th and 6th of June, we have a couple more front crossings. So we're able to do a pretty good job of finding these ocean fronts using the MCTS algorithm and getting the scientific data that we need. And we wanted to be able to look at a quantitative way of measuring that. Before I get into that, I want to talk about, right, actually, yes, so I'm going to get into that here. So the quantitative measure of this that we used is front crossings per kilometer. So kilometer is distance traveled. Front crossings is sort of individual times it crossed an upwelling front over those kilometers. Now, this isn't a perfect measure, because if you're getting a lot of redundant data, front crossing might not be useful. But generally, I think this is a pretty good measure of how well the algorithm is doing. We do this sort of with the ship and without the ship. That doesn't really matter too much. That's just whether we're using the ship data or not. The ship crossed the front quite a bit. The ship was controlled by the MCTS algorithm. We had the captain look at the trajectories and put the ship where the trajectory told it to, where the autonomy system told it to. So both with and without the ship, you see that under manual control, we get a certain number of front crossings. And in some of our autonomy experiments, we're doing better. We're getting more front crossings per kilometer. And in some, we're doing slightly worse. And this is really what we were looking for. This is what we wanted. So we have competitive performance in terms of front crossings using the autonomy algorithm as we would with the operator control. So this is a really nice result. We're really excited about this. The other thing that we found that was encouraging was that the acceptance rate of the plans, the scientist always has the opportunity to reject a plan if they don't want to run it for whatever reason. In the preliminary autonomy testing, they were rejecting about 25% of the plans, either because of safety or because they weren't really going where they expected it to. But then as the experiment went on, it started rejecting fewer and fewer plans. And we were close to 100% acceptance ratio for almost all of the autonomy testing during experiments 1 through 3. And ultimately, that one rejected plan, I think, was because it got too close to a ship that wasn't necessarily in the planning software. So it's important that we have this override capability from the humans, but we also see that we have pretty high acceptance rate, and it's not really necessary for the human to override it very often. So this is also an encouraging result. So ultimately, we were able to identify a front and track its motion across an 18-hour period during the longest experiment. Over the course of the experiment, we identified about 3 upwelling fronts, which was great. And what we found was that this was fairly competitive with the human-driven experiment in terms of mapping error and uncertainty. And if you're interested in the full results, in terms of like how well the Gaussian process worked or how we did the parameter selection and all those other details, I'm not going to get into today. Happy to answer questions about that, but also direct you to the JFR paper, which gives sort of everything that happened there. Cool. So that was sort of the main segment of the talk. I'm already at a half hour in. But I also wanted to talk about this other aspect of marine robotic decision-making and collaboration with the operators. And that's the idea of semantic navigation. And so what we're trying to do here is we're trying to interact with the operators on a more fundamental level. So in the previous section, when we talked about the heterogeneous information gathering, there was an MCTS algorithm, provided trajectories, there was an objective function that was developed sort of in collaboration with the oceanographers, but there was really no good way for the scientists to provide instructions for what the vehicle should do. And what we want to be able to do here is we want to be able to have a language instruction, something like sample the upwelling front, routing to the east of the island, using the gradient of the salinity field as the objective. That's an instruction, so it tells the robot what to do. We want to turn that into plan constraints that become an executable trajectory. So here's an example. This is the start for robotic vehicle and the end for robotic vehicle. This is the trajectory that it takes. It's trying to do information gathering. It wants to monitor upwelling front Bravo. For instance, it may be routing to the right of Shaw Island or the east of Shaw Island. Northeast of Shaw. These are various different constraints that could be imposed by an operator in a language instruction. And so for information gathering tasks, we need to set these non-intuitive constraints and reward functions, and language instructions sort of provide a natural way to do that. And what we do is we look at semantic features. So for instance, left of the island is a semantic feature as opposed to a metric feature that provides an interface for robots and humans to understand each other. And so what we have developed here is a semantic feature detection algorithm for upwelling fronts. We're still going to talk about coastal upwelling fronts as our area of scientific interest. And also a framework to map language instructions, like this one here, to the constraints and the rewards that robot planners would be able to use to optimize. And ultimately what this leads to is a topology constrained information gathering algorithm that is able to operate based on semantic language instruction. So the first step is to convert language instructions to plan constraints. That's that step there that you see in the red box. And then we're going to, in order to do that, we're going to use the Stanford parser to extract the universal dependency tree. So I'm not a linguist, but we're able to use some of the tools that linguistic AI researchers have developed. And then we're going to translate that linguistic relationship into a spatial relationship using a rule-based framework. And that's going to allow us to generate a trajectory. So first, let's talk about the parsing. So let's say I have this fairly simple instruction, go to the southernmost upwelling front. Well, the Stanford parser, what it can do, or any parser really, but the one we're using is a Stanford one, is go is the root of the command. Front is where you're going, where the command is going to. And then you have various different modifier words. So southernmost is an adjective modifier of the front. Upwelling is also a modifier of the front. And then you have to and the, which are sort of transitional words that help the understanding in the tree. And so ultimately, we can talk about the action. So that's go, that's a move action. We can think about where you should go. So that's what your upwelling front. Southernmost will tell us which upwelling front we want to go to. And then there's sort of the connections between them are based on the other words in the tree. So the destination, so the action is move, the destination is upwelling front Bravo. And then what we can do is we can convert that into an information gathering path. And the way that we do that is, again, using a robot planner. So traditional information gathering problems like this one here, this is sort of the standard framework for informative path planning. We're trying to maximize some information objective subject to some budget constraints. In our information gathering problem, we're trying to maximize some information objective subject to a budget constraint, but also subject to constraints in topology. And so we want the topology of the trajectory to match the route that is specified in the language instruction. And the way that we're going to do that is by defining the constraints using homotopy classes. So we're going to use topology to define these path constraints. So for instance, the constraint might be route to the north of the island. Paths A and B are in what's called the same homotopy class. They can be deformed into each other without cutting or without crossing an obstacle. Whereas path C is not deformable into path A and B. So path A and B satisfy routing to the north of the island, whereas path C does not. And so using those homotopy constraints, we can translate these language instructions into more understandable homotopy classes, which can then be used as constraints for the informative path planning plan. And then we need to optimize the trajectory. So we're going to use a similar approach to what we did before. So we're going to generate a probabilistic roadmap by just sampling a whole bunch of points over the environment and connecting the ones that can be connected using a local planner. Then we use Dijkstra's algorithm to construct what's called an augmented topology graph. And so what that tells you is it tells you which of those nodes are in the same homotopy classes. This is going to be very useful in terms of finally planning the path. And then we're going to use Monte Carlo tree search again from the start node to generate the final trajectory. We already talked about kind of how we do that in terms of building up the tree and looking at different partial trajectories. So the other thing that we need, the last piece of the puzzle, is we need to be able to automatically detect semantic features in the environment. And so the most important features here are the scientifically interesting features, which are the upwelling fronts. And so what we did was we collected data labels from a bunch of robot deployments at different times of the year. And then we also used data from the Regional Ocean Modeling System, which is a collection of model output that synthesizes satellite data and drifter data into a view of what the ocean looks like. And so, for instance, this is a snapshot of salinity from 2011 that we can download from the internet. There's a CSV file there. And what we want to be able to do is we want to label areas that are part of a front and not part of a front. And so in order to do that, we employ a convolutional neural network method. We also developed a support vector machine, a more traditional method as well, to see how much advantage we'll be getting from the CNN, if at all. And so the data, we looked at two different data representations, these sort of more details, but there's an overhead path representation and then a slice representation. And we could use either of those as input to the CNN or the SVM. And what we found was that we were able to get pretty good results from the upwelling front detector. The best results came from the slice representation in the CNN. This is nice for people that are working on deep learning. Yeah, CNN is still better than SVMs in these kind of domains. And we're able to get, in terms of true positive rates, close to 95% with only about a 15% false positive rate. So the true positive rate really quite good, false positive rate fairly low. And so this allowed us to automatically detect upwelling fronts in the data and provide those semantic features to our algorithm. So what we wanted to do is we wanted to test this framework. We automatically generated about 1.1 million language instructions using kind of a Mad Lib type instruction template. And you might say, well, this is a little bit restricting. But ultimately, for our framework right now, what you need to do is you need to give the scientists kind of a template of how they would give instructions. We can't deal with all possible language instructions. That's a huge space. But if you give them sort of a few templates of instructions, they can work within those templates. So we generated 1 million of those from 10 different phrasal templates, 850,000 route following instructions, sort of go to multiple different waypoints, and 300,000 information gathering instructions, like monitor this front, those kinds of things. And what we found was that about 80 to 95% of the time, we were able to get a valid semantic mapping out of that, basically be able to generate a trajectory that met the constraints and it was correct. We did have the algorithm requested clarification for about 10% of the route of the instructions, and was then able to generate a valid trajectory. It was kind of like, did you mean something? Because something was unclear from the parser. And then there were a few that failed. And those failure cases were situations where either sort of ambiguous words were used, English can actually be quite ambiguous, or things were not specified in a way that the parser was able to correctly track. Most of those issues were actually from the Stanford parser. Parsing language is actually very difficult. But some of those might also have been from the upwelling fronts being incorrectly classified and those kinds of things. So failure rate ultimately fairly low, success rate fairly high. And so ultimately we were able to do this on this sort of set of 1 million different instructions. And then we also wanted to try it out with real instructions from oceanographers. So we got 3 mission descriptions from real glider missions that were undertaken at OSU. And in sort of ocean science speak here, let's translate these. So fly OSU 683, 684, 686. These are the call signs for 3 different gliders. 2 kilometers south of the NH line, that's a latitude line. Starting at NH1, that's another line, going to NH30, with the initial waypoints being the offshore point. So we're going to start at an offshore point where the vehicle's deployed, and then we're going to have some path constraints relative to longitude-latitude lines, and then also distance constraint as well. And then we have 2 sort of similar commands that are basically how we would control these vehicles. And so here's what it looks like. So here's the 3. So 683 is in sort of pink, 684 is yellow, 686 is that sort of blue-green. And here is the expert design path. So this was the trajectory that the vehicle actually ran in the mission. This was the path where there were sort of no topological constraints. It was only considering sort of information gathering. And you see that by using the topological constraints, we are able to get a trajectory that abides by these instructions. So for instance, looking at the expert design path, we are sort of in the right homotopy class, in the right sort of topological equivalence for all 3 of these trajectories. So not only does it work on sort of the randomly generated corpus, but it also works in these 3 sort of case studies in terms of translating real commands. Now, the next step in terms of what we're interested in here is we're also interested in explainability. And thinking about if the robot plans a particular trajectory, being able to explain to the operator why the robot chose that trajectory. And so that's something I'd be happy to talk about, but those results aren't quite ready for prime time yet. So that's the main section of the talk. I'm just going to take a couple more minutes and also talk about some exciting new areas that we're looking at that are related to underwater robots. So this is another project that's ongoing, where we're trying to do docking and recharging of an underwater vehicle. And the advantage here is that this is an oscillating dock in the Hinsdale environment, and this is an autonomous docking procedure. You can see the fiducials for the localization of a vehicle that's able to move into this dock sort of its own accord without any teleoperated control. And once it's docked, it's able to use wireless charging, like how you charge your iPhone, in order to recharge its battery from a wireless charger that's positioned in the dock. And in the ocean, the dock can use wave energy. So it can harvest energy from the waves and from the ocean currents in order to recharge that battery on the dock and then recharge the vehicle from that. And so what this has the potential to allow is will allow vehicles to be resident in the environment without ship support. So I mentioned that, $30,000 to $50,000 a day, that's what we want to get rid of. And so this is another capability that's necessary in order to do that. And so we're developing the autonomous docking capabilities for this as well. And then lastly, those of you who know me or know my work know that we usually gather information, don't really intervene. Well, this is an example of some work that we're doing where we are intervening. We are grasping in the environment. So this is an underwater arm in the Hinsdale Wave Lab. This is a 3D point cloud built from an underwater stereo camera that our collaborator designed from scratch. Notice it's a bit noisy, so the challenging perception conditions. And what we were able to do is we were able to grasp these various different objects. So for instance, in like an environmental cleanup scenario, here's a gas can. We're able to do this fully autonomously. So from the 3D camera, we generated the point cloud, did graph synthesis using a CNN-based network, and then used sampling-based trajectory methods in order to generate a trajectory that had a high chance of success. Now, of course, things are not perfect. Here's an example where the arm grasps an outlier point. It basically is grasping at ghosts. It's not really part of the object. Here's an example where the gripper actually slid off the object. So this object was a bit too heavy and a bit too slippery for the intended grasp to work. So here it attempts to grasp this propeller and doesn't work, right? So there are failure cases as well. However, with this coral and sort of environmental sampling application, we did actually have a fairly high success rate. So we're able to get 4 or 5 successes over 5 trials in the environment. So these are just a few examples of some of the things that we're working on and some of the underwater marine robotic decision-making applications. Lastly, so for those of you who aren't familiar with Oregon State, if you're an undergrad looking for a graduate position or a graduate student looking for a postdoc or a postdoc looking for a faculty position, Oregon State University Robotics is really a great place to be. So we started our PhD program in robotics in 2014, really modeled it a lot after CMU. So if you're familiar with the CMU program, then OSU is really quite similar in terms of requirements and those kinds of things. We have 16 core faculty, about 80 graduate students, a bunch of affiliated faculty in areas like computer vision, also oceanography, forestry. Those folks are interested in using drones, agricultural science, interested in monitoring type applications. So great affiliated faculty across the university. Got this cool high bay space where they're testing the fire alarm today. I don't know if you heard that earlier, but this is where my office is right here, over there on the top right. And so you can see we got a lot of robots in here. And this was sort of the artist's conceptual design. Looks pretty close. And we also have a new building, the Collaborative Innovation Complex, which is breaking ground soon. We're going to be able to do full-scale drone testing in a sort of augmented reality environment, which is pretty cool. That's sort of one of the facilities that's going to be in this new building. With that, I want to thank O&R and NSF for funding this. Seth McCammon, absolutely fabulous PhD student who's now tenure track at Woods Hole Oceanographic Institution. He was the lead on the first part, the heterogeneous multi-robot coordination. Ian Rankin, who just did his thesis proposal, will be graduating soon. He's doing the semantic navigation for the second part. And then a number of faculty collaborators as well. Kip, Jonathan, and Jack are all oceanographers, so that sort of shows the collaboration on the project. And then a few other PhD and master students helped out on this work as well, and also participated in the cruise, which was a lot of fun. So with that, thank you for your attention, and we move to the discussion.
All right, thank you so much. It was a great presentation. Yeah, so we'd like to move on to some questions. If you have a question, you can either enter it in the chat. If you're on YouTube, enter it in the chat there. If you're in person on Zoom, you can go ahead and raise your hand and we can call on you. I guess first, so we could go to, there was one question on YouTube, and we believe it was for slide 23, just the graph that was comparing the results. And they were wondering if you could elaborate on the bar graph and to see specifically if it was comparing the number of valid paths determined by people versus software. Yes, this one, I think this is it.
so the table, or so the bar graph is front crossings per kilometer. And the table is these sort of accepted plans by the humans. So I guess what was the question?
We could, I don't know if the person is still on, they can clarify in the chat if this is the right graph first off, but maybe we can come back to this if Christy's still around.
Okay.
I think we have Basti. If you'd like to ask your question.
Yes. Hey, Geoff.
Basti.
Nice talk. I had a question on basically the dialogue management part. So you had this you had this clarification part. How did that work, and how?
Yeah,
that was done automatically, right?
Right. So I did kind of skip over that. So basically what the parser takes the instructions and it translates them into constraints. And sometimes the parser is able to say that it's not sure, like there are multiple different dependency trees that could be valid and it doesn't know which one. And so then it can ask for clarification. So basically if the parser spits out multiple dependency trees and says, could be this, could be this, could be this, then you can ask which of these is what you meant. If sometimes the parser spits out a tree that's wrong, then you don't necessarily know that you think that you've generated a correct parsing of the instruction. And so it really has to do with what the output of the parser looks like in terms of whether you can ask for clarification. Now, it would be possible to run an additional post-processing step that checks again for like common misconceptions, things like that. You may be able to get that rate down even more.
So you're essentially always trying to get a feasible, well-defined problem, and if you don't have enough constraints or something, you'll ask for clarification.
Yeah, so like English is ambiguous. I'm trying to think of a good example. So it's like if there are two islands that are next to each other, and you say, like, say you have island 1 and island 2, and you say go west of island 1. And you don't mention island 2, it's ambiguous whether the instruction means you should go between the islands or east of the island. And so it may generate a tree for both, or if the islands have like concavity and stuff in them. If the geometry is complex, it may be sort of underspecified. And so sometimes you want to ask for clarification on that. That's one example. And then, but there are other situations where there's ambiguity in the language.
So then, but then that clarification, so there must be another kind of generating thing on the end there that generates that clarification, right? Because it seems like you're doing this over, like, I don't know, hundreds of thousands of cases, right?
Yeah, so we're able to generate that clarification in the way that we do explainability, which I didn't talk about because that's newer work. And so we are able to explain the trajectory to the human using a different framework. And using that same framework, we can take the dependency tree and say, basically, did you mean this or did you mean this? By rephrasing what the human said and saying which of these is what you actually meant.
Okay, thank you.
Yep, and I mean, if you're interested in more information on that, Ian can send you more of the details.
Yeah, I would be very curious. Thank you.
Cool.
All right, it looks like we have a question from Sung Chung. Best to unmute you.
Oh, hello. Thank you for the great talk. I have a question regarding the semantic and topological context constrained path planning. Like there was an example you showed there was instructions that like route to the north of the island, and path A, B satisfies the condition that the path is going to the north, and path C doesn't satisfy that condition. Like, could you clarify how exactly that like topology like constrains the path planning of the motion? Like, yeah, there was like homotopy classes. Like, how are the like path planning being constrained by that? Like,
yeah, absolutely. Yeah. So a homotopy class basically is defined as two paths are in the same homotopy class if they can be continuously deformed into each other without cutting. And cutting means moving through an obstacle. So for instance, if I were to take B and I were able to, and I sort of pulled it, you'd run into the island. Basically, the island would stop you from deforming B into C. And so that means that B is not in the same homotopy class as C. And so what we do is we translate these language instructions to a particular homotopy class. Like, for instance, north of the island defines a homotopy class, south of the island defines a homotopy class. Things do get a little bit, that's where some of the ambiguity can go in. The C class is also east of the island, and A and B are also west of the island. So, but you can define a homotopy class from those different instructions.
I see. Okay. Yeah. Another quick question regarding semantic navigation. I think this question overlaps kind of with Basis's questions, but like, how subtle difference does the semantic language interface handle? Like, for example, if the instruction is go to the southernmost upwelling, does that what about go to the south of the upwelling? That's very subtle difference, but it's different instructions. How could the semantic interface can handle those differences, like those subtle differences?
So that example it should be able to handle. So go to the south of the upwelling, it would translate that as a homotopy constraint to be south of it. Whereas go to the southern upwelling, it would go to the the southmost upwelling. That should be translated properly. Now, where there would be ambiguity there is go south of the upwelling. You may not know which upwelling. If there are multiple upwellings, you wouldn't know which one to go to the south of.
Okay. Yeah. Thank you.
But we're kind of at the mercy of the parsers. We're not linguists. We didn't program our own parser. And so if the parser spits out garbage, then the robot's going to execute garbage. So if the linguists do a good job, we can do this well. If the linguists don't, then it's a problem. And it is limited to the templates that basically those 10 templates. If you give it an instruction that's completely outside of the template, it might work fine, or it may just completely fail.
Got it. Thank you.
All right, we're going to circle back to Christy's question. So she clarified on the slide, I guess 21. She said she understands what the bottom table is, but she wanted some clarification on what the two colors represent in the graph and also in relation to the table below. Definitely.
Okay, so the orange is without the ship. So those are front crossings purely from the gliders and the surface vehicles. So if you're getting you can basically identify a front crossing. I can't remember if we did it automatically or manually here, but you can identify a front crossing automatically, or you can identify a front crossing just by looking up the data. And I think we did it automatically, but then we checked it that, we got rid of any false positives or false negatives by hand. So what the orange is number of front crossings per kilometer traveled by the assets. So by the gliders and the surface vehicles. Blue includes the ship. So we had a ship, it was the RV Pelican. The chef was amazing. He was from New Orleans. We were in the Gulf of Mexico, so it was all Cajun food, delicious. So we had a ship, and we actually had our planner deciding where the ship should go. And so the ship was also a controlled asset. And the only reason that we set these apart is because, people may say that using the ship is cheating because it wasn't really fully autonomous. There was a pilot on the ship. So if you really just want to look at full autonomy, you can just look at the orange bars. And basically all we're trying to show here is that if you look at, manual number of front crossings is about 0.1. In two of our experiments, we outperform that. You want more front crossings. You want to see more of the upwelling fronts. That's the scientifically interesting feature. And then in one of the autonomy experiments, we do a little bit worse. So basically it's competitive, or we're competitive with the human trial. And then in relation to the bottom graph, in order for the asset to run a trajectory, it needed to be approved by whoever the scientist in command was at the time. We had two shifts. There was a day shift and the night shift. And so we had basically a chief scientist on both of those shifts that was approving the plans. And if a plan was rejected, it just simply wasn't run. And so the rejected plans wouldn't be considered in the front crossings per kilometer because they were just never executed. Basically, what would happen if a plan was rejected is the planner would run again, and then the next plan would most likely be accepted. The reason that we had that is because there are things that the planner is not necessarily aware of that the human may have better context for. And we wanted to make sure that we weren't doing anything that was unsafe or that was just sort of clearly the wrong thing to do. But as you see, it wasn't very often that happened. So And in the initial shakeout testing, we had a few rejected plans, but once we kind of got things up and running more smoothly, it was very unusual for there to be a rejected plan. I also feel like, you know, it is a little bit misleading because what happened was that the oceanographers got comfortable with the system and they got used to it doing good things. So once it had seen 41 plans that they were happy with, they're kind of like, yeah, it looks good. I'm going to go have my lunch, you know, like, so there was a little bit of ambivalence. And I think the trust in the system definitely increased to the point where maybe it was an overestimate of the system's capabilities. But that's another interesting aspect of the HRI aspects and the human robot interaction is in terms of how the humans interact with the system. The other thing that, you know, truth in advertising, they're not using this anymore. They went back to manual control because that's what they're used to. And these deployments are really expensive and they have the operators to do it because they don't have a huge number of assets. And so, you know, ultimately, this was not super useful to them at the scales of experiments that they run. And they really want to have really, really minute control over what's going on. And so that's something that's very valuable to them. So I really think that this will make a huge impact if we do try to scale up the assets to, you know, hundreds, because you're not going to be able to coordinate those assets with humans. You need autonomy. But for the sort of small deployments that are going on, I think the scientists are going to prefer just to do things themselves. So
that's a really interesting point. We have time for one last question. And this one, it looks like it's from the Zoom chat. It says, the underwater manipulation task looks cool. And I'm wondering which component is the bottleneck in this challenge? Localization, state estimation, perception, or planning? And then also, how does information gathering help in this task?
Oh, that's a great question. Yeah. So I could give another talk on the manipulation. It's super exciting. It's just, it's newer work. So we're not, quite there yet. But what I will do is we have an ICRA paper that's coming out on that manipulation. So let me share that in the chat. And that'll definitely be a great reference. But I can also speak towards that question as well. Hold on, let me get this in the chat. So if you're interested, this is the place to look. Now, I think the perception is very difficult for sure. And I'd say right now, the limiting factor for us is perception. And the reasons for that is because the underwater environment, perception is more challenging underwater than in terrestrial environments for a few different reasons. You have turbidity, water cloudiness. Notice in that example, the water was clear because it's in a test facility, but in the real ocean, water can be very cloudy. That can be very challenging. You have a lot of specular reflections and transients in the environment, sort of reflections that are moving back and forth due to waves and due to sort of the ocean conditions. That can be difficult. And then you also have issues as you go deeper with the light refraction changing the color space. And so anything you're doing with RGB is also going to be challenging. You have to sort of adjust the color space for that. And there are people who've worked on that, and nothing's going to be perfect. And so that's going to be difficult. The localization and state estimation becomes very challenging if you take the arm off of the test bed. Notice that we had that on sort of a fixed test bed, so we knew where the test bed was, and put it on an ROV. Then trying to localize that ROV is very, very challenging. And so that then becomes the bottleneck unless you are sort of fixed and you know your position. The planning and the trajectory optimization actually and the control is pretty well understood because there are a lot of really great people that are doing manipulation in terrestrial environments, and we can kind of use sort of similar techniques. So they're all challenging. They all have sort of, different aspects in the underwater environment. But take a look at the paper if you're interested, and that'll kind of give you a sense of what the domain is like. Okay, thank you so much. We're at the end of time. Thanks again, Professor Hollinger, for doing this. And I guess if anybody has any additional questions, they can reach out to you through email is probably the best way. Yeah, absolutely. Email me, and happy to send you links to papers and stuff like that. And happy to talk if there's something that overlaps with your research as well. All right. Thanks again. Have a good day. Thanks for having me.